All right, so ladies and gentlemen, welcome back. This is part 2 of this video. This is us practicing using kind of torque, moment of inertia to try and determine how we can get things to turn. So this practice question I asked you to kind of get work started on before we ended the first video is I wanted you to kind of figure out how much torque it'll take to turn this bolt with the wrench that we're using. And then we want to figure out how much force that means we need to use in order to produce that torque. All right. Now there's two parts to this. The first part, we're going to use our relationship for Newton's second law for rotation. All right, and I've written it right here. It's the idea that the torque that needs to be produced is just dependent on the moment of inertia times the angular acceleration, which remember that symbol would be the alpha, the little fish. All right, now that means that literally we're just multiplying these two things together. So the torque, looking at this, is just going to be equal to the moment of inertia, which is 2, times the angular acceleration, which is 5. So 2 times 5, congratulations, is 10, which means the torque that you have to produce is going to be 10, and here's the unit for torque. It's something a little bit weird. Newton meters. All right. So that means you need to provide 10 Newton meters of torque in order to get this bolt to start turning. All right. Now, the next piece is that we use this torque to calculate how much force that kind of equates to for us. So it says my hand is 20 centimeters from the bolt. All right, and how much force do I need to apply to turn the bolt? So basically, that means the wrench is on the bolt, and my hand is 20 centimeters away from the bolt, which would basically say that, for in this case, the length of the lever would be 20 centimeters, or that little R. And I want to figure out how much force I need to apply in order to produce that torque. Now, I make it very clear that I apply the force perpendicular to the handle of the wrench, which means that the angle will be 90 degrees. So let's plug in some stuff that we know, just like we always do. Remember, whenever we try something new, always look at the question, just plug in what you know first. So I now know the torque. I just found it. So the torque that's being provided is 10 Newton meters. All right. I don't know the force yet. That's what we're looking for, so I'll leave that as F. I now know that R, that distance from the turning point, in this case, is 20 centimeters. So, of course, that needs to be in meters. And then I know that sine of theta is 90, so that's just equal to 1. So that means for us, we're left that the force, basically the amount of torque is just 10 Newton meters. It's going to equal some force we don't know yet, times 0.2 meters. All right. So if you go through and plug that into your calculator, you should get, and if you should have gotten, if you kind of work through that, that the force you're going to have to apply is going to be equal to, I believe, 50 newtons. And I can check, let me just check real quick, just make absolutely sure. But right there, what we're just seeing through as we work through this is that the rules are very similar to everything else we've talked about so far. All right, force, torque, same thing, one's just causing something to turn. Acceleration, angular acceleration. Same thing, just one's causing something to move forward, one's causing something to move in a circle. Moment of inertia and mass, kind of similar. They're still a little weird, but that's okay. We're going to keep practicing it. All right, so 50 newtons is exactly right. So right there, we've kind of just seen this idea that torque and force are related to each other, but they're not necessarily the same value. All right. Now, this is for only one thing producing a torque. Let's look at this next question. All right. Now, let's say I have a cylinder of mass 50 kilograms. All right. The moment of inertia of this solid cylinder is represented by this formula right here, which you'll notice it says the moment of inertia of a cylinder is 1/2 times the mass of the cylinder times the radius of the cylinder squared. We want to figure out what the rotational acceleration produced by the two forces is going to be. So we're trying to find alpha. All right. Now, basically, you can look at this as two different strings are trying to kind of pull on this cylinder, trying to get it to turn. But if we kind of look at what's going on, you'll notice that there's kind of some weird stuff happening. All right. Now, if we go through our problem solving process, drawing an FBD here is going to be a little bit strange because it won't make a ton of sense at first. So I'm actually not going to draw my FBD for this particular one. But instead, what I'm going to do is I'm going to identify my two torques because I have two things that are trying to get this to turn. So the first thing that is trying to cause a torque is going to be the 70 Newton force. All right. And what we do to identify torques is we try to identify them based off of if they're going to cause the thing to turn clockwise, which if you're not sure what clockwise is, it means it's going like this. or torque that produces counterclockwise rotation, which means it's going to go like this. All right. So just to be clear, clockwise, left to right, counterclockwise, right to left. So let's look for clockwise torque first. So I'm just going to call it TC, clockwise torque. Only one of those two forces is providing that sort of torque, and that would be the 70 Newton one. All right. So we can see the 70 Newton one is producing a clockwise torque. We can probably calculate it, but we might not need it just yet. But we'll just kind of identify that it's the clockwise torque is going to be 70 newtons times how far away it is from the axis of rotation, which in this case is 10 centimeters. It's rotating in the center. So, and it also makes a right angle with that lever arm, so to speak. So the angle is going to be 90 degrees. So it's going to be 70 newtons times 0.1. So that's a clockwise torque. Now, the other thing is going to provide counterclockwise torque, and that's going to be the 120 Newton force. All right, and right away, you should already start seeing that of the two forces, these are probably not balanced, which means it is going to start turning a specific way. All right, so the counterclockwise torque is by the 120 Newton force, and this one is 15 centimeters away, so 0.15 meters. Now, this is where we kind of use the same kind of process we use for Newton's second law with linear motion. We know that the angular acceleration is going to be equal to the net torque divided by the moment of inertia. All right, and that comes straight from right up here. If we look at our relationship, angular acceleration is represented by alpha. If I get it by itself, it's just torque divided by moment of inertia. So the same idea is here as well. The angular acceleration is going to be the net torque divided by the moment of inertia. All right. Now, at this point, I want you to pause the video and I want you to solve it. All right. Because I think we've covered enough about how to look for the net torque that the rest of it, I'm pretty confident you can set up. So you're going to need to use this formula for moment of inertia, but pause the video, take as much time as you need. Once you think you have an answer, come back, we'll talk about it. All right, so hopefully you had a chance to kind of work through this and get some sort of angular acceleration. If you calculated the moment of inertia, which I hope you did, otherwise you're probably not going to get an answer, you'll get that it's a kind of a small number. It's going to be a moment of inertia of about 0.5625. So we know that our alpha is going to be equal to the net torque divided by moment of inertia. So the net torque is going to be basically all the clockwise torques added together minus all the counterclockwise torques added together, or vice versa. It's just this, it's like going right minus left or left minus right. It's really up to you. Okay. I'm going to do the clockwise torque minus the counterclockwise torque. So I'm going to say the clockwise torque is going to be 70 newtons times 0.1. So that would be about, I believe, 7. All right, Newton meters minus the counterclockwise torque, which is going to be 120 times 0.15, which when we go through and do that, that's going to be 18 Newton meters of counterclockwise torque. And then we're going to divide it by the moment of inertia, which in this case is, I believe, it's 0.5625, and there was that weird unit at the end. I don't really care about it. All right. So when we go through and calculate all that, we get that the angular acceleration is equal to approximately 19.56 radians per second squared. And what we can say is we can either say negative if we want to do that, or we could say, to make it very clear, you can say that angular acceleration is that value counterclockwise. So we make it very clear that it is turning counterclockwise. But that is indeed undergoing acceleration because it has an unbalanced net torque, and we're going to explore in more detail what it looks like when the torque is balanced the next classwork. Okay. Now, the last two pieces on here are both practice problems I want you to work through. They're both kind of looking at the idea of moment of inertia and the idea of torque and all that kind of goes with it. So what I want you to do is I want you to kind of pause the video and I want you to answer these two things. Then we'll come back together and talk about what the answers are. But this moment of inertia question is probably going to be a little strange at first. One thing I want to point out is that all three of these objects are the same mass. That's really important. And I want you to kind of pay attention to where it looks like all the mass is concentrated. And remember, the farther out the mass is, the larger the moment of inertia. All right? Now, the second question with the torque can be a little bit simpler. You're basically ranking the 4 forces that are being applied to this object. You're ranking by how much torque they're probably producing. All right? Pay attention to where the axis of rotation is. It's right here in the center. But with that being said, ladies and gentlemen, pause the video. Try and give yourself some answers to the 2 questions, and then when you're ready, come back and we'll give the solutions to both of them. All right. So hopefully, ladies and gentlemen, you've had a chance to work through both of these. So let's talk about the moment of inertia question first. Very strange question, all right, because I didn't give you any formulas. You could have definitely looked it up if you wanted to, but what we can do is just kind of visualize what it means to have a moment of inertia. So in all 3 of those cases, I am rotating that object around its center point. Okay, so the axis of rotation is in the center. Now, they all have the exact same mass, but it's very clearly distributed differently looking at the 3 objects. Okay, so actually, I'm going to go in reverse. I'm going to start with the least, all right? Of the 3 objects, the one whose mass is kind of spread out and not farthest away is actually B, all right? Because even though B has the same mass as the other 2, because it's spread out through the whole disk, a lot more of the mass is close to the center rotation point, so you don't have to use as much force, work, whatever you want to call it, to turn it. All right, so B is actually going to be the least. Now, next is going to be A. All right, because all the mass is located in that ring, which means all of the mass is much farther away from the axis of rotation than in part B. All right, but the catch is that A is still not the highest moment of inertia, because if you drew A over top of C, you would actually observe that C is farther out from the center of rotation than A is, which means this moment of inertia is even greater because the distance the mass is from the center point is farther away. All right, so in this case, the ranking would be, it would start with C, then A, then B, due to the distance the mass is from the axis of rotation. And honestly, that is what I want you to get out of talking about moment of inertia. I'm not really worried about calculating it. I'm not really worried about all the nitty-gritty about, well, you know, a cylinder has this, a sphere has this. What I am focused on is the idea that we can look at this and visualize the idea that the more mass that's farther away from the turning point, the harder it is to turn because it has a larger moment of inertia. All right? Now, the second question I asked you to work through, hopefully you got some answers for this practice question. So I've got 4 forces trying to produce a torque. And I say trying because it's not necessarily true that they're doing that. Okay? So let's start. I'm going to start from least to greatest because there might be a couple that are already 0 we don't have to do anything about. So we know that for a torque, we have to have 3 things. So torque equals the applied force. All 4 of these are applying a force, so we got that. Times the distance from the axis of rotation. All right, in all cases looking at it, they all have that as well. Times the sine of the angle that the force makes with basically what you can consider the lever arm. All right, now this is where we might be in business. If we look at those 4 forces right away, you should hopefully notice that 2 of them are not actually going to turn this object at all. This hexagon is not going to turn based off of those things. And that would be D and B. In both those cases, for D, the angle would be 0. For B, the angle would be 180. But in either case, sine of that angle is going to equal 0. All right, because it's parallel to the axis of rotation, or it's parallel to the lever arm. So we start with D and B, they're not producing any torque. So we're left with A and we're left with C. Now, C looks like it's a pretty promising thing, except it's not perfectly perpendicular. So C is not producing the full torque that it can. A, on the other hand, is perpendicular to the lever arm. So A actually maximizes the amount of torque that's being produced. So the ranking is going to be A, then C, then B, which equals D. All right? Now, in all these cases, ladies and gentlemen, and I'm almost out of time, so I'm just going to wrap this up. These are all practicing the idea of just the same stuff we know, but for a rotating system. So with that being said, ladies and gentlemen, have a great rest of the day, and I'll talk to you later.